After 6.9 years, or 2,518 days to be exact, our solar panel array has produced 100 megawatt hours of electricity. This is the spreadsheet that I use to keep track of all of the stats relating to our electrical system, and I have used this graph to inform a whole bunch of graphs that I'll be going over later in this video. But I just wanted to show you right here that on July 5th, our system finally produced 100,000 kilowatt hours, or 100 megawatt hours, over the course of its lifespan. At the average rate for electricity of 10.95 cents per kilowatt hour in Utah in 2017 when I designed my grid-tied system, that is $10,950 worth of electricity. After tax rebates, our solar array cost $9,735 to install, and it broke even at day 2,256, or 6.18 years. If you'd like more details about the cost of the installation, I will include a card above to the playlist of several videos going over the installation costs of the two phases of our grid-tied rooftop solar installation, which I installed myself to save on costs. As of July 5th, 2024, the solar panels have produced $10,950 in value, which is $1,215 more than they cost to install. There is likely going to be some maintenance cost, like replacing the inverter once over the lifespan of the solar array. The inverter warranty is for 12 years and the solar production warranty is 25 years. When the time comes that I need to spend money on replacing components, I'll add that to the installation costs. Only when the entire solar array has been removed or replaced will it be possible to calculate the exact price per kilowatt hour over the lifespan of the solar array. Up to this point, I've had zero maintenance costs since the installation went online in August of 2017, so I am truly getting free electricity from the sun. Over the warranty period of 25 years, the panels will have paid for themselves 4 times. I calculated that by dividing 9,131, which is the number of days over 25 years, by 2,244, which was the number of days it took my system to break even. It's likely the system will continue operating past that point, as I've heard many panels working for 40 plus years, or perhaps not, only time will tell. My solar array is 9.98 kilowatts of solar panels, which I installed in 2 phases. I installed 6.38 kilowatts in 2017, and I made that array a little larger in anticipation of getting a Nissan Leaf, which I purchased in early 2018 with the tax rebate money. Then in 2019, we purchased our 2015 Tesla Model S 7-seater, which has much longer range than the Nissan Leaf, and thus can use more electricity, so I installed an additional 3.6 kilowatts of solar panels on our house. Over these 6.9 years, my goal has been to use all of the electricity our panels produce. Not more, not less. That goal is razor thin and frankly nearly impossible to achieve, but I have been as close as 8 kilowatt hours one year. The reason for this goal is the way our electricity utility net metering agreement works. Any excess electricity that we push into the grid is credited to our account and it rolls over month to month until our March bill each year, at which point if there's excess electricity on our account, it's reset to 0 and we are not compensated for the excess kilowatt hours. I really don't mind this agreement though, because throughout the year we have unlimited transfer of electricity into or out of the grid for about $10 per month. So for $120 per year, the grid is our unlimited battery where we store up excess electricity in the grid during the high producing months for the dark winter months. We are grandfathered into this net metering agreement until 2035, and at that point I will assess the market and likely install battery backup for the entire house so as to avoid the excessive fees of the current net metering agreement. Here's hoping battery prices have come down in the price nicely. If you have been following my channel for long, you probably know I like to experiment with my technology to see what's possible. Back in 2021, I installed 2,650 watts of flat-mounted solar panels on the roof of my travel trailer RV, which I use to exclusively charge our Model S when we are not camping in the trailer. Right now, that experiment has been going on since March 3rd, 2024, where I've charged our Model S only from the trailer, and we have put 1,990 miles on our Model S in the 5 months since then. I'm going to be making a dedicated follow-up video to that experiment someday when I decide to conclude that experiment, which might be in the fall of this year when the solar production gets low enough, or perhaps I'll go for an entire calendar year. I haven't decided yet. Not charging the S from our house has lessened demand on our house net metering balance. Plus, now that we have the Model Y with unlimited supercharging and there's a bunch of new superchargers relatively near where we live, we are exclusively supercharging it. The reason is to extract the money back from Tesla that they somewhat coerced from us back when we purchased the Model Y, which I'll put a card to above if you'd like those details. In short, the Tesla employees lied or were mistaken and said that we'd get the inventory discount stacked with the free supercharging transfer. Then when we went to the Las Vegas service center to pick up our Model Y, the employees down there said, no, we can't get that inventory discount, and would have to pay an additional $3,378. I was close to walking away from the deal, and in hindsight we should have, because the very next quarter Tesla did stack the inventory discounts with supercharging transfers, but there's no way I could have known that was going to happen. In any case, Tesla is playing irritating games with their promotions and not standing behind their employees' mistakes, so we're getting our money back as soon as possible by exclusively supercharging our Model Y. From the research I've done regarding battery degradation, supercharging does not appear to be as big of a problem with these 2170 cells in the Model Y compared to the 18650 cells in our Model S. And there are now multiple superchargers near where we live compared to 5 years ago when we got our Model S. After 7 months of owning our Model Y and with 13,500 miles on our odometer, our supercharger bill would have been $1,438, so we've recouped 42.5% of the additional money Tesla charged us for the free supercharging transfer. Tesla does not display anything relating to supercharger costs in the car since it's free, but I want to know what it would have cost us. I found I can go into the Tesla app and download the charging history of our vehicles. I then export that as a spreadsheet and use that to calculate the money we would have paid. Annoyingly, some states don't allow Tesla to bill by the kilowatt hour, so it's a convoluted time block rate that I have to calculate a bunch of additional calculations to get the total. This is the spreadsheet that I exported from Tesla for just the Model Y for 2024. And this is the most recent charge up here at the top, and then the oldest charge is down here at the bottom from January 1st. And so just in brief, you can see that the normal billing that Tesla does that is by the kilowatt hour, which is how it is in most of the United States, they just say what the quantity was in kilowatt hours, and then I can take the unit cost and multiply that out, and then this right here is the total. So it makes the math really easy. Unfortunately, for those states that don't allow Tesla to bill by the kilowatt hour, we have to do this convoluted quantity tier thing. So this is in quantity in minutes. And so this is hard to see. Every row here that you can see there's a gap over here, that's the row that I inserted in order to do my calculations. So what they gave me is there's an NA in a lot of columns because I guess I didn't use any quantity of that time tier. But this one I used 6 of that and 12 of that, so that's 6 and 12 minutes. So then I can come over here to the cost tier, and I can see that it was 43 cents per minute for tier 2, and it was 71 cents per minute for tier 3. So I can do a calculation here, which you can see is multiplying that 6 for tier 2 to the cost for tier 2 of 43 cents, and that's where it came up with this figure of $2.58 for that piece of the tier. And then this one right here is the same calculation but for tier 3, and then over here is the total for that charge session. So that's what you can see is being repeated all the way down here on each of these lines. So it's annoying to have to do all these additional calculations, but that's what the state legislature is making us do because they won't allow Tesla to be a utility and basically provide electricity by the kilowatt hour. They make them bill by the minute because of their laws in that state. Because neither of our electric cars are being charged from our house, our net metering agreement is right now at 3,000 kilowatt hours and is most certainly going to achieve an all-time high balance this year. Last year it got up to 3,087 kilowatt hours on October 30th, 2023 before it started to trend down, and in years prior to that, typically around 1,200 kilowatt hours was what our net metering balance would peak at before we went into the winter. On January 1st, 2024, I plugged our 5,600 watt or 18,500 BTU electric space heater into our clothes dryer outlet, which I've used in years past to convert excess solar energy into heat in our home to reduce our natural gas bill. This year, I used it all waking hours when someone was home until the net metering balance reset on March 6th. I managed to get our net metering balance down to within 58 kilowatt hours of zero, which is a win in my opinion. Here's a graph from our natural gas utility provider, and you can see a significant reduction in natural gas consumption January through February. The big dip in April is because we were out of town on our 3-week, 7,168-mile road trip in our Model Y, going to Key West, Florida, and many places in between. I'm excited to share that video series with you all, but alas, video editing is really time consuming. But don't worry, I'll get that video series published as soon as I can. Last winter, I very nearly didn't use all of our excess electricity soon enough. So this winter, I'm going to begin using the electric space heater right at the beginning of the heating season. Then when my net metering balance gets down to around 1,000 kilowatt hours, I will discontinue using it until January. The space heater has been an effective and cheap method to use our excess solar electricity, but it's only 100% efficient instead of closer to the 350% efficiency of heat pumps. The obvious next step is to install an air source heat pump in the place of our existing air conditioning compressor. And I will most certainly do that as soon as our existing compressor is at the end of its useful life. Unfortunately, that won't be for a while yet, since we installed it in 2016 before I had any idea I'd be installing solar the next year. I can't financially justify replacing a perfectly functioning AC compressor, so I'm just waiting and using the space heater in the meantime. I wish I could do a ground source heat pump, but we don't have a big enough yard for that, plus it's far more costly to install. In past videos, I've reviewed graphs I made which illustrate various aspects of our energy consumption versus production. So let's look at those graphs updated to this new 100 megawatt hour production achievement. This is the first of the graphs that I wanted to show you today, and this is part of a series of graphs that I created in a prior video years ago, and I'll put a card above to that video. And now this has the additional years added since then. And what you can see here is just the solar production, and so that's where it starts out here in August of 2017. And then you can see the solar production declines as we go into the winter, and then as we proceed back into the spring and summer, then the solar production increases, etc. And that's this constant up and down curves, the seasons. And then right here, there's a step change where it jumps up. And you'll see that about right here in May 10th is when we bought our Tesla Model S. And so we started to need more electricity. And this, of course, graph doesn't reflect that at all because this is just the solar production. But this is where I added additional 3,600 watts of solar panels on the roof of our house. So it jumped up. And then now there's this continued pattern, but it's the step change with the increased solar panels on the roof. And what's interesting to me about this is that you can see that, well, it's pretty noisy looking, I get that, but each year is not an identical replica of the last. It's quite varied, actually. When you zoom in on these years and look at them in other interfaces, there's a large variance. In any case, that's where it ends is today. So now I'm going to switch over to the next graph, and this is showing all of the electricity that is being consumed by our home and thus our electric cars whenever they are charged from our home. So this is the same date range as that prior graph. And you can see here at the beginning there's a bit of a spike, and that is primarily because it was still in the warm season of the year and we were using a lot of electricity. And then it drops off as we go into the fall and winter, and we're using less electricity as the weather cools off. And then you can see here there's this increase as well as we head into July of the following year. And basically, you're going to see a similar up and down pattern, but this is now consumption. And this consumption is driven by air conditioning primarily. Although the electric cars, this is the beginning of 2018 right here. This is around when we got the Nissan Leaf. But we ended up charging it, or I ended up charging it from my work more than at home, actually. I didn't realize that there would be a possibility initially when I was planning this solar system. In any case, this is reflecting all of our energy consumption combined as we go throughout those seasons. Whenever you see a big downturn like right here or over here, these are when we go out of town and we're on a trip. So we're away for a while and our energy consumption is obviously lower because of that. In fact, you can see a huge dip over here, and that is when we went to the Florida Keys and we were gone for 3 weeks. So that's a long period of time. That's why there's a big dip here while we were away for that time frame. Now you'll notice just prior to that there's this huge increase in energy consumption, and you'll notice that this is in February, so that's not air conditioning, right? Because that's middle of the winter. And this is what I was just talking about earlier, where we had a lot of excess electricity on our net metering balance, and in March we have to use it or we will lose it. So we were using the electric space heater to heat our home, and so our energy consumption was quite high while we were obviously burning off that excess electricity. But we were not just burning off, we were putting it into our home and offsetting our natural gas consumption. So that's that there. Otherwise, this is just several years of our household energy consumption and all the spikes that are associated with that, potentially for various reasons when multiple things combine on one day. Like some of these really big spikes would be we drove a lot, so the car needed to be charged a lot, and maybe we were driving the next day as well, and it got charged a second time, and then it was maybe a really hot day, and so there was a lot of electricity going to the air conditioner. And then some of these days too, maybe we were running, like we have a freeze dryer and it uses a lot of electricity or various things like that. So there's this right here is the absolute peak, and that is 134 kilowatt hours consumed in one single day, which is a lot. Prior to our going solar, our average daily was 20 kilowatt hours a day, or actually just shy of that. So this is many, many, many times more than that. But obviously electric vehicles make for a lot of spikes. You can kind of see all these really narrow spikes. Most of those are probably when we are charging our electric car a lot that day. This is our average daily consumed, and you'll see that in the very beginning it was heavily driven upwards because of our electricity consumption for air conditioning in the late summer there. And because we didn't have a lot of history yet, basically the average drove up pretty quickly. And then as we headed into the fall, you'll see it dropped off here pretty precipitously, as obviously we were using far less electricity due to not using air conditioning. And then it bottomed out down here in March, and then in May it started to go back up again as we started to use air conditioning again. But you'll see it's now normalized a little bit because we have more data to go off of, so the average stays lower. And then this continued curve up and down is driven by the seasons, air conditioning versus no air conditioning, and it's leveling out pretty nicely as it has more and more years of data to go off of. And so now our average is 38.88 kilowatt hours per day over the last like 6 or 7 years. And keep in mind, our average prior, like I said, was 20 kilowatt hours a day. So we have more than doubled that, but really our consumption now just matches our production from the solar panels by and large. And as I've talked about, I have various ways of making sure to use all of that electricity. So now this is the two prior graphs of the daily solar production and the daily used, but this is the two combined into one graph overlaid. And so it's even more busy looking. There's a lot of data to look at, I get that. But really what I'm showing here is that there's a huge variance between when the consumption occurs versus the production. The production is a lot more consistent, right? You can see these curves of the black lines, that's the solar production. And yet the energy consumption spikes like crazy on some of these days. Now this, for people that are grid tied, this isn't necessarily a big concern, at least not in our case, the way our net metering balance works. We can transfer as much electricity in or out of the grid, and there's no additional cost to us. As long as we have energy credits there, we can use them. And it's just a flat $10 a month to transfer that electricity. I get that other net metering agreements with other utility providers are different, and so you'll be incentivized differently. And that's why I'm pointing this out. If you were to add a battery into this, like a whole house battery, then you would, if you were completely off grid, you'd want to be kind of curtailing your consumption. Like some of these spikes, we just, with reckless abandon, just plug in the car and charge it all the way up if we need to. Whereas if you were living off grid, you'd charge the car as much as you have energy to give it, because you're limited by the daily production as well as your energy storage capacity of your battery. And so I just kind of an interesting overlay, I think, if you're going to be going off grid, or if you want to limit your transactions of electricity with the grid, that to see what we've been doing with electric cars and just living, you'd have to be living your life a little bit more within the natural production capabilities of the solar panels. Monthly produced versus consumed. So this is kind of self-explanatory, but you can see per month the black column is how much was produced by the solar panels, and then the red column is how much was consumed by our house. And so you can see that in certain months the black is exceeding the red, and that's where we're in the spring and solar panels are producing more than we're consuming because air conditioning hasn't kicked in yet. And some months it's quite significantly that way. Oh, and this one's, that's August. That's interesting. So it's a hot month, but we used less air conditioning, I guess, and so our production was higher than the consumption that month. And this one actually here is a really big difference. That's June. So that's a springtime month. So a lot of solar production and very minimal energy consumption. And so that's just kind of what it looks like for us. Oh, and then over here on the other side of the coin, you have, say, November, where we're consuming a whole lot of energy and we're producing very little. So that's where the red bars are way above the black. And in this case, if I remember correctly, this is when I was using that electric space heater to heat the house. And so I was burning a lot of excess electricity during that time frame. And then you'll see over here, This is January 2024 and February, and I did the exact same thing, but I did it later in the season because this year I kind of went overboard and ended up having to buy a little bit of electricity in like February of that next year. So this year I did it later in the season, and then that one was where I actually almost didn't burn up enough electricity by the time our March cycle came around. So that's where this year I'm going to start it in the early fall, like in October, November. And once I get down to around 1,000 kilowatt hours of excess electricity in my net metering balance, then I will switch to waiting until February to burn off that remainder, or maybe January. We'll see. We'll see how it goes. Now down here, you'll see I said monthly before solar average consumption. So this bar right here, where my mouse is pointing, is 584, and that is the monthly average energy consumption for about 2.5 years prior to us installing solar panels. So that's this level down here is what we were normally living off of prior to solar, and now we have all this excess solar that we now consume. And then here, monthly after solar average consumption. So now you see that my average after solar has nearly doubled, pretty close to doubling. And so obviously we could have gotten by with less solar panels, but with the electric cars, we actually did have increased demand, and that's all mixed in here, meaning what could we have gotten by with if we didn't increase our solar panels? It's hard to say, because now our consumption and our production largely match, and so that's just the way we're doing it. And then this next graph over here is solar average monthly production. So you can see that's how much on average our solar is producing. And keep in mind, this average right here is not our 9.98 kilowatt solar array only. It's over here, it was 6.38 kilowatts, and then we made it bigger, and then now it's bigger. So this is kind of an average of both of those systems over that time frame. And then over here is Utah's average household electricity consumption. So our average was already below what the state's average was, and now this is the state, and now this is what our average is because we have now solar. Okay, so daily net grid. And so this is showing on a daily basis how much electricity is going into the grid versus coming out from the grid. Like what was the net for the day. So as an example, if you have a really sunny day, then we're going to be putting more into the grid, and that's one of these spikes here where it's up high. And this zero where it would be just breaking even. And then if you're in the winter months, then you potentially are consuming more from the grid than you are putting into it, and that would be these drops down here. So that's December, for instance, we withdrew 95 kilowatt hours net out of the grid. And the most extreme example of that is right here, 104 net out of the grid on February 5th. And so February 5th of 2024, you'll see the production was only 4.27 kilowatt hours. I was thinking it might be zero, maybe snow on the panels, but 4 is pretty close to zero. And so we obviously consumed a lot that day, but the solar didn't do anything, so the grid made up the difference. So you can see kind of the cycles here, similar to the others, whereas the seasons come and go. And in the spring, our net grid is going up, and then in the fall and winter, definitely it's coming down. So that's kind of interesting to see. And then you can see also here the huge deficit that we're running in the January and February timeframe of 2024 as we're running down our net metering balance with that electric space heater. So then if we move over here to net grid, this is showing that same information, but more of an average or net over time, cumulative, rather than just looking at the daily amount. This is showing how much we are going, pulling out energy from the grid versus putting energy into the grid and coming out of the grid, going back into the grid, coming out of the grid, etc. So that gives kind of a visual representation of just our transfer into the grid. And this next graph, this is now showing our net metering balance with our utility. So this here, initially we went into the negative in September. Our net metering agreement was new, our solar had just been installed, and it wasn't producing as much as we consumed, so right here, this jump where it jumps up, anytime you see that, that's where we actually had to pay for that electricity on our monthly electric bill. And then here, each of these red dots is when we get an electric bill from our utility, and it shows what our official net metering balance is. So the rest of this line is all of my spreadsheet and my estimation, and the red dots are the official numbers from the utility, which you can see largely line up, but it's always off by just a few kilowatt hours. I suspect there's some variance there of when I was reading the meter versus when the utility was, just by a few hours. And so that declined down our net metering balance. And then March, it used to be that our net metering balance reset in the end of March, and so that's where this was. And then you can see that our balance climbed up again the next spring, and then went down in the fall and winter. And then here, a couple of times we had to pay for electricity. You can see 3 months in a row we had to pay a little bit of electricity. So 361 kilowatt hours, 234, and 187. And then coming over here, you can see we got really close this year. So you can see we got down to 38 kilowatt hours remaining on our net metering balance. And then finally it started climbing up. And then by the time the April bill came around, it was at 534. But if we hadn't had that climb, we would have had to pay for electricity. And so there were a few times here where it went into the negative and then came back up. And this one was the closest I've ever been. Oh, I guess it was 6. So I had to pay for 6 kilowatt hours of electricity that year. That was February of 2021. And then here our net metering balance reset and we lost 18 kilowatt hours the next month. And then it continued up and down all the way through these years. So I just find this really fascinating to see. Now you'll notice that there's this big step change over here with these 2 towering mountains and this third one that's starting to begin. And the reason why the net metering balance is getting so much bigger than it used to is because of the solar panels on our RV. Those are now offsetting. It's basically that much more that we have. You could think of it as kind of like being on the house because we're using it for charging our electric cars. And so now they're not pulling energy out of the house as much anymore. So before, if you look over here, we were peaking at around 1,000 or 1,200 kilowatt hours. I think over here, yeah, that's about 1,200. So between 1,200 and 1,000 kilowatt hours is what we were peaking at. And that was generally sustaining us as we went throughout the winter each year. But now it's jumping so much higher. You can see here it peaked at 28, and this over here it peaked at 3,000 kilowatt hours. And right now we are right at 3,000 again. This graph isn't quite showing. There it is. It's actually 3,000. It's just not quite showing here. And so we're going to exceed the prior year's peak this year, I'm sure. That's where I'm now using that electric space heater to burn off all of this excess electricity to heat the home and offset our natural gas bill. That's the best thing I could think of to do with the electricity. So that's what this graph represents. It's one of my favorite graphs, I think. So now we have the cumulative produced versus cumulative consumed. So over the whole time, the cumulative amount of electricity that our solar panels have produced and then how much electricity we have consumed over that same time frame are overlaid on top of each other. So you can see they match quite well, but if you look really closely, you can see as an example right here, there's the yellow, the solar production is just a little bit higher than our consumption during that time frame. That was in June, July, August. Here you can see there's starting to become bigger variance, and you'll notice that this yellow and red and this yellow and red deviation, it matches with these giant mountains right here. So basically our solar production is getting to be so much higher, our net metering balance is getting much higher compared to our consumption, that it's a noticeable amount on this cumulative graph. I mean, keep in mind when we get here to the top that we're up to 100 megawatt hours of electricity that's been produced, and then our consumption is really close to that. So anyway, that's my last graph. I thought I would show you. I think this is all interesting to me. I hope it's interesting to you too. In summary, I'm very happy I installed solar panels back in 2017, and now with an expanded array on my house as well as on my RV, and having electric vehicles has been an amazing experience, and I intend to continue experimenting with the technology I already have, as well as whatever new technology I acquire in the future. I hope this has been helpful to see how this electric technology is working for us, and if you have any questions about our grid-tied solar panels, RV electrical system, Model Y, Model S, electric space heater, or anything else, let me know in the comments section below. With that, thanks for watching, and I will see you in the next video.